Morning, Professor. My voice is audible for you?
Yes.
Shall we start the session?
Yes. Just give me a sec to go live.
Yeah. So good morning to everyone. On behalf of School of Information Technology and Engineering and Department of Computer Application and Department of Smart Computing, I invite you all for this guest lecturing on the overview of different chart types with Matplotlib. So I request all the students to be this presence, which take an immense pleasure to invite our today's chief guest, Professor Atanurao Chaudhary, who is an founder of CapGuard, and he is a technical functional consultant for IoT and artificial intelligence. He is a technology advisor for the Ranveer Foundation and its incubator. He is a part of board of mentors at the Atal Incubation Center from Sikil Manipal University and KL University. He has a postgraduate degree in computer science from IIT Guwahati and Harvard University. He is a senior member of IEEE and CSI chapter, and he's bringing over about 17 years of experience, professional experience. So on behalf of School of Information Technology and Engineering, I welcome you, Professor.
Thank you. Thank you, Professor Jyotish. Thank you for the warm welcome.
Yeah. Now I request Professor Atanurao Chaudhary to take over the session. Please, sir.
A very, very good morning to all of you who are joining us today. Right. The session is also being live cast on YouTube. So those of you who cannot join in here, you can view into our live session. Right. We got a little delayed, but let's make up for that. Today's focus, today's discussion, I wanted to primarily break it up into 4 aspects, right? I wanted to talk about an overview of what data visualization really is, right? And then I wanted to get into the anatomy of a figure, because at the end of the day, when you are creating a visualization, that is your playing field. So you need a solid understanding of what are the controllables in that figure itself, right? We are going to look at some basic charts and how do you annotate those charts, primarily where you are plotting very relatively simple data. And finally, we are going to look at some advanced visualizations, which might be more useful when you are using data to tell a story, right? When you are trying to bring out the insights from a particular data set, right? So without further ado, let me get started, right? So the first question itself is, what is data visualization, right? And data visualization for me, it's kind of a process of representing data and information in a visual format, right? So even if you think about this presentation that I am making, I am putting my thoughts in a form which is easier for me to communicate using, right? So that's why even that is a visualization, right? But we generally tend to think of data visualization as using charts, graphs, maps, or some kind of diagrams, right? So the fundamental process of data visualization involves transforming some raw data into visual elements that can be easily understood and easily interpreted by humans, right? So if I can summarize that, then the primary purpose of data visualization is to communicate complex information, patterns, or insights in a visually and intuitive manner, right? Now, when we do visualize data, there is, it has to have some objectives about it, right? So what are the key objectives of data visualization? Well, one way of looking at it is exploratory analysis of data, right? So what we call data exploration and analysis, right? So visualization allows analysts to explore and understand data more effectively by visually examining patterns, trends, and relationships, right? It helps us to kind of uncover hidden insights and facilitates this data-driven decision making, right? What else happens? Data visualization is important for communication and presentation, right? Because visualization makes it easier to present data to an audience, right? Whether it is to your colleagues or in a classroom setting or in a sales pitch, right? Wherever it is, if you are having to present data to an audience or to even to a general public, right? By presenting the data in a visual format, a lot of complex information can be simplified and conveyed more effectively, right? Because pictures tend to express a lot more, right? It can also be used for pattern recognitions and insight generation, right? So this is where a lot of statistical elements start to come in the visualization itself, right? The way you represent a particular information can easily help identify, patterns, trends, anomalies, correlations, right? And which may not be easily comprehensible when you look at the data in its raw form, in like columns and columns of data, right? But by presenting the data visually, these insights, these upticks, for example, there's a little uptick over here, so you clearly know that something happened over here, right? So it kind of brings out these important insights really quickly, and it's easier to recognize and understand, right? The third, or probably the fourth aspect of data visualization is probably around storytelling and creating narratives, right? Because as you parse through the data, right, it can tell you a story, or it can convey you a message, right? By carefully selecting the visual elements, you can bring out those aspects. And finally, the reason we are doing the data visualization is ultimately to be able to make a decision, right? At some point, we are doing this visualization because we want to know if something is good and something is bad, when to do something, right? If something is to be done, and that is decision making. So data visualization kind of enables this data-driven decision making by providing a clear and concise representation of information, right? So that's very, very important, right? By visually comparing and analyzing data, right, what you can do is you can make informed decisions about the process, right? Since we are talking about data visualization, let me break that up a little bit, right? So data and visualization, right? And as you have probably guessed from the picture itself, I wanted to talk about data visualization tools, right? First of all, you need something to write your program or your analysis software in, right? I personally prefer doing that in Kaggle, right? You can all go into the website www.kaggle.com, set up an account, and you can write your own code on it, right? One of the reasons I prefer using Kaggle is because every time you start up a new kernel there, it's a fresh kernel, right? So you are not, if you have had dependencies that has built into your Python environment, right? You can avoid that by using Kaggle, right? The second advantage is you can move your data to the Kaggle environment itself, and then process it on that data set itself, right? Even possibly be able to share that information with other collaborators so that you can work on a data set effectively, right? So remember, data is king over here, right? So once you have the data, you can start processing on it. Of course, you're free to use a lot of other tools, VS Code, for example, Jupyter notebooks, right? All of them are equally good. Comes down to how comfortable you are with a particular environment, right? So once you have an ID and environment kind of set up where you're going to write your program, right? Let's take a look at some of the key tools that you may need in Python itself, right? So the first thing is definitely the base Python software, right? The Python compiler and everything that needs to be up there. One of the key libraries that you will be using quite a bit is the random library and the maths library, right? So they allow you to do basic processing, functional calculations, right? All of them can be easily done using maths. And in many cases, when you are sampling the data, right, you may need to use the random library to pick out one data from your data set, right? So it tends to get used quite a bit, right? And along with that, you also need to generally have a sense of being able to navigate your data files and all of that. So file IOs are going to come into the picture, your directory walks, finding out where a particular data set is located, right? So all of those are going to be essential aspects of visualization, right? The next tool you tend to use quite a bit is NumPy. NumPy is particularly useful when you are using numerical data, when you are processing large sets of numerical data, right? The advantage of using NumPy, and those of you, you have had your previous classes, you already know that you can use a list to store a set of numbers, right? Then why use NumPy? Well, in NumPy, the basic data structure is a NumPy array, right? Which means that all the data points are kind of co-located in the memory itself. So accessing the array is a lot more efficient when you are dealing with large data sizes, right? So maybe if you are considering 100 elements, 200 elements, 500 elements, you might get away with being able to use lists and similar data structures. But when you are dealing in thousands and hundreds and thousands of data points, then NumPy is a very, very good friend to have, right? Now, in many cases, the data that you will be handling is not necessarily only numeric, right? You might also have a lot of text fields and strings that are coming in, right? A lot of enterprise data that you will see will consist of alphanumeric values. There could be names, there could be order numbers, there could be quantities, all of those could be involved, and that is where pandas comes into the picture, right? It allows you, it's got its basic data structure, which is a data frame, and the data frame can be manipulated in the internal memory, right? So you can create a data frame or reassign a set of data or some information into a data frame, and then use that as your primary data structure to process your graphs from. So pandas also very, very important tool to, especially when you are processing alphanumeric or text heavy data, right? Now, in many cases, you may also need to look for insights into the data, and you may need optimized statistical libraries, right? Maybe you may not need it for calculating means and medians, but some of the more esoteric functions you might want to use something called SciPy, right? Also a very popular library and also a friend if you are going to be using Python for machine learning and number crunching like that, right? Then, of course, we come to our most important library for today, which is Matplotlib. This is where everything else centers today. It is a library that you essentially use for creating custom plots, right? And something that you can use to highlight insights from the data sets, right? I'm going to talk about the grammar of graphs in a little bit that forms the kind of foundation for Matplotlib-based applications, right? Now, while Matplotlib can help you create a lot of charts and graphs, it's not very good when it comes to handling representations like social networks in general, right? And that is where you have another tool called Network X, right, which allows you to kind of represent and analyze graph data. Right? So if you are doing sentiment analysis or social media analytics or any kind of network effects, then they might be easier visualized with something like Network X. Now, apart from Matplotlib is it's been around for a while, and it's got a lot of pros and cons. It's very, very customizable. That is why we kind of tend to use Matplotlib significantly. But of late, there have been a few more visualization packages that have been created for Python, right? So this includes Bokeh, right? Bokeh is a library that provides kind of interactive visualizations for web browsers, right? So it allows you to kind of create these interactive plots, dashboards, right? And data applications with a relatively concise and straightforward syntax, right? So it supports things like line plots, scatter plots, bar plots, The next one is Seaborn, and Seaborn is particularly good for visualization of, it's based on Matplotlib itself, but has a much more simplified interface for, generating slightly prettier graphs more easily, right? And especially when it comes to handling statistical data, right? So it kind of provides a high-level interface for creating pretty attractive and informative statistical graphs, right? And it kind of simplifies the process of creating complex visualizations, right? With a lot of built-in themes and color palettes. So that's the advantage of Seaborn, right? And then this is also coming up becoming very, very popular of late, called Plotly, right? Also an interactive and browser-based graphic library that allows you to kind of create interactive visualizations, right? And the advantage over Bokeh is that it supports a wide range of chart types, including, whatever we have covered before, along with a lot of heat maps, a lot of 3D plots and things like that, right? And Plotly can be used both offline and online, right? And it offers kind of a Python API so that you can integrate directly and display using Plotly. So now that we have covered the data visualization tools, right, I wanted to talk a little bit probably about the data sources, right? Where is the data coming from, and how are you going to access that data, right? So because if you have to process the data, the first thing is the access to that data itself, right? So of course, the data can come in from multiple locations, right? One of the most straightforward things is getting the data from a database. You write an SQL query or an unstructured query, right? Or you query an unstructured database. You will get this data either in the form of, the data will be kind of sent over to you, right? So it can be sent over in binary form, or it can be sent over to you as a file, right? If the database is kind of behind a backend server, you will get the data as a file, right? So when the data comes in, the file can be of different formats, right? It could be a raw data, right? Raw data in the form of texts, right? So when you are getting the data in the form of a text file, or as a comma separated value or a tab delimited value, right? Here, what you are expecting is some kind of a header information in the data, and then essentially rows and rows of just the data elements, right? So that's typically what a CSV file, a comma separated value file is. Even if it is an Excel file, you'll get data in that format, right? The other way you can get data is where it is structured, right? It is a little bit more structured, and you get the data in the form of, say, either JSON or XML or some proprietary format, right? With JSON, what you are getting is a key value pair, right? So instead of just having a column of, say, names, you will have a key called name and a value called, say, Atanu. You have another key called name and a value, say, Jyotish, right? So this is how you create a name value pair. So the description of the data is also part of the, is in the file itself, right? So those are key value pairs. And in both these cases, you have to read the file, and then parse the relevant data for your plotting, right? And of course, there is another way of having access to data, which is essentially kind of simulating your own data, right? So you kind of write a little program or a simulator that throws out statistically similar data, or statistically similar to what the real life use cases would have been, or it is just made up data for the purposes, of creating a visualization, right? So if you are reading, say, for example, a raw file, right? If you are looking at a text file, typically a text file or a CSV file, typically what you will expect is a data set like this, right? Where you have the headers that are up there, and values that are either, space separated or comma separated or tab separated, right? Reading these files is relatively easy. You can upload the file. If you're using Kaggle, you can upload the file in your working directory, and you can either use the read CSV file or you can do a file IO operation, right? By which you can essentially import the entire file, read it line by line, and put the relevant fields in your custom data structure, right? Or you can create a pandas data frame using this, right? So that's one way of doing the data, right? What we are going to be discussing today, for the sake of moving ahead in the discussion, I wanted you to look at, if we were to create or simulate that data, right? For today's discussion, I'm going to simulate a data where we essentially have about 6 fields, right? The first field is a sequence number. It is an integer. It's a unique integer. The second field is a student ID, right? Student ID is also a unique string of the form ST and numerical, right? You have a gender identification, which is a string, right? An M or a F. You have scores, mid-semester scores out of 30. You have final scores out of 70 and total scores out of 100, right? So those are what we call are the dimensions of the data, right? So there are essentially 6 dimensions in this data set, right? So we'll take up our examples based on this particular use case, right? So when we are building a simulation, we have some constraints. Say, for example, we want to create a data set comprising of probably say 50 students. We may have a constraint saying that minimum marks is 0, maximum mid-sem marks is 30, maximum final marks is 70, right? So total marks is, of course, the sum of both of them, right? And your maximum total marks is 100, right? So those are the constraints. Since we are building a simulator for writing this code, we can have a rule which says that gender is to be allocated with 50% probability. Your mid-sem marks are going to be allocated based on a normal distribution. Why? Because generally whenever we have physical processes, right? For example, scores, it tends to exhibit a Gaussian distribution or a normal distribution, right? So we can simulate the same kind of classroom marks distribution by saying that it's going to look like a normal distribution with a mean of 15 and a standard deviation of 6, right? Which means that most of the marks are going to be between 9 and 22, right? And what you can see is I can very easily, I can create a distribution like that using NumPy's random variable, right? And I can say a random of type normal. I can give it a mean. I can give it a standard deviation and the number of samples I'm looking for. So number of students. So I can use this line of code to essentially create a allocation for the midterms, right? And I want to say that there is some correlation between the mid-sem marks and the final marks, right? So let us assume that the final marks are typically a multiple of the mid-sem marks plus minus some deviation, right? So that way there will be a correlation. Somebody who scored very high in their mid-sem marks, it is very unlikely that they will score very low in their finals, right? So we expect them to be the more studious students, right? So we have kept just a, for the sake of proper simulation, we can keep a correlation built in, right? And I'm not going to get into the details of the code for generating this, but I'm going to leave it on the screen for a couple of seconds so that you can come back to it at a later point and look into it, right? But essentially, we have created say a list for each of the variables that we will be using, right? So including mid-sem marks, end-sem marks, total marks, student labels, gender, and then we have created a loop where each of those elements are being generated. Yes.
Can you visualize, zoom the particular code?
I'm just going to leave it up there. This is not very important code, right? Just know for sure that here what is happening in this code is because I needed to plot these elements at some point, I'm just going to create a separate, list for each of them. And the allocation of values to that list is going to be based on these constraints, right? So just know that for the time being, right? For example, I've taken, I had to make an allocation of gender, and I'm just randomly flipping and picking a gender like M or F, right? So that's one way of allocating. Now, supposing I have that data set, supposing I've created that data set, right? So what is important is that I have this data set where I have a sequence number, student ID, gender, mid-sem marks, a final marks, and a total marks, right? So let us assume that we have been able to create this, or this was already available in an Excel file or a CSV file, and I have read it and created my five lists, right? So as to put it. And I want to plot this, right? So what is the basic function of plotting something with Matplotlib? Well, it is as simple as saying that import matplotlib.pyplot as PLT or any other name that you choose, right? And I want to plot. So plot is the function that I'm going to use. So plt.plot, sequence number, total marks, and color I have put as Capsule Labs blue, right? So some CL blue that I have defined, right? And what I have here is a plot of I have the sequence numbers which are in the x-axis, and I have the total marks in my y-axis, right? So that is a plot. That is about as easy as it is to show a plot, right? Just these two lines itself, right? But as you can probably tell, this graph does not really convey any meaning, right? It does not tell us anything. I can see that there are some jagged edges, some jagged lines that are there, but it does not tell me anything because this graph is not annotated, right? So there is no accompanying information with this visual representation, right? So the first thing that we need to understand is, what are the controllables in this particular figure, right? What are the things that we can do over here? And there are multiple controlling knobs that you have, right? But first, let us understand what are the things that can be changed, right? There are many things that can be changed over here, right? So I have a list of what I call the anatomy of a figure. And if you go to the Matplotlib tutorial, I've taken this example from the tutorial itself, right? So there are multiple things that can be controlled, right? How am I going to control this data set? So the first thing that we need to know is this border line that we have, right? This whole border, this is what we call as our figure, right? And when we set up the figure, instead of arbitrarily picking up a figure, we can give it a variable, we can give it an argument of fig size, which tells us, what are going to be the dimensions of that figure, right? So this is a squarish figure, so you can clearly say that my fig size was a square dimension, right? So plt.figure allows us to set the dimensions of the figure, and this is the canvas on which your plot will be built, right? The next thing that you have control over is this title, right? So that you can give your plot a specific name, right? And you can do that by using the set title variable, right? So set title, if you are using one plot, you can do plt.setTitle, or if you have a subplot that we will talk about a little later, you can set the title of an axis as well, right? But notice that whatever you want to put on the top of the figure is what your title is, right? The next thing is your axis, right? You can add an axis to your graph, which essentially says, you can add an x-axis. You can set a limit on that x-axis, right? You can set a limit saying that this x-axis will go from 0 to 4, right? And it has to be equidistributed, right? So you have a control of creating an object called an x-axis. Since you can create an x-axis, you can, as you have already understood, you can also create a y-axis and set a limit on top of that, right? So this allows you to control how far your y-axis will go. You can now set a X label, which is essentially the reference point or the units of the variable that you are representing on your x-axis, right? So in our example, we had student sequence number or student ID. That was our x-axis, right? So we can set a label for the x-axis itself so that it gives a viewer an understanding of what is happening, what grows or decreases along the x-axis. Similarly, the counterpart to that is the y label, right? What is the label? How do you want to label the y-axis, right? So in our previous example, y-axis, the label of y-axis should be scores, so, or marks, right? Something like that, which is which is an understanding which tells the viewer what is mapped in the y-axis, right? Then you have a concept of major ticks, right? So the major ticks are where these grid lines are set up, right? So if I have, say, for example, I have already set the x-axis to be from 0 to 4. And if I say that I have a multiple locator of 1, which means that I'm going to have a tick every 1 unit, right? Since I can set the x-axis, the ticks on the x-axis, I can also set the ticks, the major ticks on the y-axis as well, right? And not only that, I can not only set up the major ticks, I can also set up something called minor ticks, right? So minor ticks are these smaller lines where I do not have a label sticking out, right? But it kind of subdivides the graph so that visually, if I have a data that is moving around over here, it very easily gives me a cue of as to what that value is, right? So I know that there are 4, that the interval between 2 and 3 is divided into 4 sub-intervals. So looking at this figure, I can easily say that the y value of this point is about 3.55, right? So it is easy, it gives me a reference point for that, right? And I can create custom y ticks. I can create custom minor ticks as well, right, along both axes, right? And I can not only set ticks, I can actually set I can actually customize the parameters, right? Whether I want the tick to be, what is the size, if I wanted it to be dotted something, for example, this is 2.50. I could have very well kept it as 2.5, right? Or I could have added a unit to it, right? So I can make those changes as well. Most of us are used to an environment where we have done this kind of charts with say for example Excel or Google Sheets, right, where all these a lot of these elements are essentially you can just click on it and make changes, right? The reason we are doing today's session is to gain a much deeper understanding of how to control the figure that you are creating. And this is important when you are going to create custom figures, right? So X-tick parameters we discussed, we have additional figures. We can bring in the grids, right? We can say that add a grid, just using the grid word itself will create a grid on the plot, and this grid will be aligned to the major ticks, right? Then of course there is the line, there is the signal that is getting plotted, right? And this you use the plot function like we have already seen, right? You can have markers of various sizes. You can put in these markers, and they typically you put in with the ax.scatter command, right? You can put it as a round, square, right? Different kinds of markers can be put up, right? Finally, you have control over the legend. You not only have control over the legend, which will map all the signals that are being presented on this slide, on this figure, you will also have control over where you want to put the legend, because in some graphs, it might be, more cluttered towards the right, so you might want to put it on the left, or vice versa, or it might be cluttered on the top, so you might want to put it on the bottom side, right? So you can decide where the location of that is going to be, as saying upper right or upper left and things like that, right? And finally, there is a spine if you want it to be bound, right? So this is the spine line that is also possible. So whenever you are creating a graph, at the end of it, remember, if you do not have a plt.show, the graph will not be displayed. So even after doing all the work, you'll not see any output. And if you have to, it's always a good practice to kind of save the figure, right? So it has an inbuilt functionality called save fig with a file name. So it will save the figure for you as a PNG file, right? So that you can use in other places, right? So that kind of gives us a sense about what are the various elements we can control in the graph itself, right? What are the control levers that we essentially have, right? Now, you have to understand that when you are looking at data, right, your input data set could consist of a number of fields. Your input data set could have fields that are needed for a particular graph or fields that are not needed for a particular graph, right? So at some point you have to convert your own input into something which we call is a graphable data, right? So you have to look at your data and decide which are the fields that are needed for the particular graph you want to show, right? And accordingly, that data has to be prepared. When I say the data has to be prepared, it has to be converted into a form that is easily understood. For example, if there are strings, that has to be converted into numbers, or there is you have your data is coming in from a string representation of floating point numbers. You have to convert them back into numbers, or if there are null values, then you have to decide what to put in those null values. So this is part of what is called data preparation, right? And then based on the graph you want to create, you organize the data into appropriate data structures, right? For example, if you want to create a line plot or a scatter plot, typically you will need two lists or arrays, one for the X values and one for the corresponding Y values, right? So, what you want to put is up to you, but you will need to have at least two arrays, two lists to hold the data, right? With more complex data types, you are trying to process multiple dimensions simultaneously, right? And for this purpose, you might need various visualization libraries that we already discussed, right? So let's go back to our example of where we created this data set for students, and let us assume that we have this data set available with us, right, which has 6 dimensions. And for my first graph, what I want to do is I want to build a pie chart, right? I want to build a pie chart which has, say, for example, the distribution of male and female students in the class itself, right? So for that, I do not need all the data. All I need is this this third column, right? The data from this column only, right? And doing that, I can create something called a pie chart, right? It's a very simple chart. What I have done is I have from my gender field, I am counting the number of M's. Remember, my data set looks like this. So this is what I call my gender. I had already created a list called gender previously, right? So from my gender list, all I want to do is count the number of F's and count the number of M's. So those are going to be my 2 values, right? So from my data, the data that I need to prepare a simple graph like this is the count of males and the count of females. And I have that by essentially using the count, the inbuilt count formula, right? So I'm running the count on the gender list, and that gets me my data. Now, for my labels, I need to have, I want to show some things, right? So for my label, what I do is I want 2 labels because there are 2 fields over here, and I have a male and a female, and I'm appending the count, a percentage of the count with male, so that I can show the data as what percentage of male and what percentage of female, right? So this data, understand that it's actually been pre-computed and put in this label list, right? Now that I have my data, which is the data list and the label list, I can use a type of inbuilt graph, inbuilt chart format within Matplotlib itself called pie, right? So I'm going to call plt.py, and I'm going to give it the data list, right? So the list of, so this data that I'm passing on. And for labels, I'm going to pass this label list, right? For colors, I have already predefined two colors, which is say Capsule Labs orange and Capsule Labs blue. So it has the hex code of my of the RGB value of the color codes, right? So I am giving it a list how to color each of these parts. And then if I want to put a title, I can put plt.title saying gender distribution of pie chart, right? So that gives me this graph, this representation. Of course, if I wanted to have three pieces, all I needed to do was add another field over here, add another value over here, add another value over here, and give it another color to represent it with. And I will have three elements being represented, or three proportions being shown on the pie chart itself, right? So the pie chart is a very simple chart. It does not give you a whole lot of information, but it allows you to see proportions very, very quickly, right? So if this was, say, equally distributed, I can very easily say that the class population is equally distributed. What the inference that I can draw from this particular graph is that the female population is more in this particular distribution, right? So that's the kind of insights I can draw from a pie chart, right? Now, in many cases, what might happen is I might want to get a little fancy, right? And I think that, this is just too much color, right? I don't like it, right? So what I can do is I can convert this pie chart into a donut chart, right? And donut chart works exactly like the pie chart, right? Except that all I have done, and you have to understand this very, very carefully, is that I have not taken away the pie chart. I have just kept the pie chart, and creating this donut is just a superimposition trick. So all I have done is I have created another white circle and superimposed it on top of my previous pie chart, right? So this is the global artist, as it is called, right? This is the global controller for a particular graph or a figure, right? So in its artist function, I have added a new artist, which means a new patch that I can create, and it is of the type circle centered at 0, 0, right? And a particular radius and color white, because my background is also white. It looks like this has become a donut, right? But it is fundamentally a pie chart. Now, we have already looked at this particular graph, right? Which is something that we created with the initial data set, where we were plotting sequence numbers, and the total marks, right? Now, very easily, one thing that you will find out is that my sequence numbers may actually start from 1, right? There may be a one-off difference between the sequence numbers, because the sequence numbers are meant to keep track of sequence. It is meant to be consecutive, right? Whereas student IDs, right, they may be consecutive, or they may skip values, right? We don't know. So sometimes it is a good practice to use the sequence numbers when you are drawing the x-axis, right? Or to, if a sequence number is not available in your data set, then to create a separate, probably a separate sequence number column there itself, right? Now that you have this graph does not, as I mentioned earlier, like, this graph does not really convey a whole lot of information. So we have to really look at what are the parameters that we can control in order to make this graph look more meaningful, right? So one way we can do that is convert exactly the same graph. This is the same graph as before. I have made a few changes to this, right? So instead of the previous plot where I had plot.show, I had plt.plot to plot this graph and just show, I'm going to add a few more things in order to control it. The basic plotting function remains the same. But the first thing that I'm going to do is I'm going to give it a figure size, right? I'm going to give it a figure size. Why? So that it kind of reflects the number of students that are there in the class, right? So the figure size, I'm using students by 2, which was 50 by 2, so 25. and max marks by 20. So the height I've kept it as 5 and the length I have kept it as 25, right? So this kind of spreads up the graph so that if I were to write something on the graph, it becomes easier and more legible, right? So for my Y label, I have put marks, right? So I have put marks, so marks shows up over here. For my X label, I have student number, so student number kind of shows up over here. For plot title, I have put total marks, so total marks shows up here. So these are the same things that we learned previously, and now I'm starting to apply those in terms of annotating the graph and making it more legible, right? I can put a margin of 1 so that these numbers don't kind of run into each other, right? So this margin is on the outside. I want to create an axis now. Why? Because otherwise my sequence number may start at 0, right? So I don't want to start at 0. I want to shift this a little bit, right? So even though the graph goes from 1 to 50, there is the graph is closed off at 51 and -1, right? Technically, it is closed off at a margin of 1, right? But I want to plot my elements from here to here so that the last element does not fall on the boundary of the graph itself. So that allows me some control over that. Then I use my basic function, which is to plot a sequence number and total marks in the color CL blue, right? And label it as total marks, right? So this plot is exactly the same as before, right? So this is the same graph as before, except that it has become a little bit more fancy. Look, this is exactly the same code. But here's the fun part. What I can also do is I want to also mark out the points in circles, in blue circles, right? So I can use again the plot function. I've used sequence number and total marks like before. And in the formatting places, I have used B and O. Now this is a short form notation for saying that mark it in blue. So see that this blue is actually different from this blue, right? And make it a circle. So that is why these circles have come up. So this is a shorthand way of doing that same quotation. You can do a RO, which would mean a circle in red, or a YO or a GO, which would mean a green circle, in a green circle, a green dot rather. Now the list of these commonly used colors is already available on the Matplotlib website. So you can have this single alphabet color representation for very, very common colors, or you can have word-based colors, right? So you can have a blue, you can have a red, right? Writing it RED, or you can define it as a variable with a hex code and use that instead, right? If it makes more sense, right? Just to demonstrate the grid, what I'm doing is I am plotting the grid function. So plt.grid will showcase the grid, and the grid, as you can see, is anchored to the major ticks, right? Now I want to do another trick over here. What I want to do is show the labels of total marks that a student received, right? So how am I going to do that? I cannot give it an array, a list. I cannot give the plot function a list saying that show all these elements. These labels, these text labels, have to be printed on the graph one by one, right? Since they have to be plotted on the graph one by one, I am going to use the text function plt.txt to indicate what is the label I want to print and where I want to print it, right? What is the x-axis and y-axis of the starting point of the writing is going to be, and then what is going to be printed. So when I am printing the value, how am I printing that value? I've taken for I in range of students, which means I am doing this for every student, and I here represents the information for a particular student ID. So when I is at 1, it is the first student. When I is at 8, it means the 8th student. So already I know that I represents these students, right? So if my first argument for the text function is I, it means that I am taking it as an x-axis of wherever this is, right? So x value is taken over here. and the y value is total marks. So y value is over here. So I now know where I am starting this, right? So I know the starting point of each of these labels, and the value that I want to be printed is a stringified version of the total marks, right? So that it is in alphanumeric, so that it is, these are characters. This is how I am able to print each number exactly at the label, at the x value it corresponds to and the y value it corresponds to, and the label is printed over there, right? So this is how all of these labels have been put together. And then if I wanted to show a legend, I'm saying show the legend in the upper left. So the legend of total marks comes up. Why total marks? Because I have already said that there exists a label called total marks, right? If I had more plots with more labels, they would all show up when I plot the legend. Finally, I'm showing that, right? So what you have over here is the same graph as before, but it is slightly more readable. It is slightly more meaningful. It is meaningful because you have a grid representation which allows you to visually see the scale of each marks, right? It makes it easier to approximate the marks looking at the grid. The values are, of course, given, and that kind of gives you, with the values given, it kind of makes the grid a little redundant, but it is still there for demonstration purposes, right? And we have the line graph, right? But what does this graph mean, right? What it is a list of student marks, right? So I still don't see any patterns, right? So there is nothing can I say that this student and this student, right? What can I say about them? Just that this person got more marks and then a student ID 03 got less marks. Apart from that, there's not much more I can say about it, right? I cannot say anything about the distribution. I cannot really make, I cannot really say anything else. The other point that I want to make here is, although this plot has lines between each of these dots, right? There is no fundamental correlation between the marks of one student and the marks of another student, right? If these marks were somehow related, if this was the mark of a same student if this was their marks across multiple years in their school career, or this was their progressive marks across their multiple semesters, right? This kind of a trend line this kind of a progression would make sense. But for the kind of data that we are dealing with, this graph may not make much sense, and which is why we might want to have an alternate representation, right? Because there is isolation between the data points themselves. So this is called a lollipop graph, and I can, I think you can all guess why it is called a lollipop graph, right? Each point, so what has happened over here is, instead of, I have the graph set up. The setup of the graph is exactly like before, right? The axis and everything is exactly like before. What has changed is that I am using, instead of using the plot function that I was using previously, I am using a function called stem, right? And stem will have the dot and the line attached to it, right? I can also create this by using plot with the O function. So if I had, if I go back to my previous slide, if I had used this function, right? If I had used this function and drawn straight lines from here, I could have done that. But this is an inbuilt function that allows me to do exactly that, right? So it is called a stem function. So just by modifying this one, I am now able to bring a different sense to this whole graph. I have taken away the temporal correlation, right? The fact, if you are having data from a machine being spit out every minute, some kind of a temporal visualization makes sense. But if there is no real correlation between consecutive data points, then you might want to use this kind of an isolated graph, right? So this is an example of what we call is a lollipop graph. Another graph that is used very, very similar to the lollipop graph, and probably what we are very used to seeing, is something called a box, something called a bar chart, right? So let me create a bar chart. And the setup of the bar chart is exactly the same as the previous charts, right? So if I look at the figures, the dimensions I've kept it the same. I have not plotted a grid because the grid was not giving me any additional information, and I still have the total marks. I still kind of have the total marks on top, right? Here, instead of using the stem function, I am using the bar function, right? So that is the only change that is coming in. I'm using the bar function, which allows me to specify. Now, whenever I'm creating a bar, I can specify where that bar will start from and how tall it will be. Where will the bar end, right? So it takes in parameters as sequence numbers. When I give it a sequence number, I know it is going to go in from the sequenced values, right? So 0, so 1, 2, 3, 4. So it's going sequence by one after another. And the height is nothing but the total marks, right? So I can as well as pass the entire list of total marks to this height parameter. So for every element, it is going to look in total marks, look at the sequence, use the sequence number to calculate which value am I talking about, and find the height value for that, find the total marks for that, and use that to construct this bar, right? Colors, of course, I can put any color I want. I've put CL blue, right? So that is why I have my blue colored bar graph. And in this graph, again, like before, we are using the text function to kind of plot the text values on top of it, right? So so far, these are all variations. I mean, I do an initial setup, and after I have done my initial setup, what I'm doing is I use 3 variants of within the plot functionality. We use PLOT plot, we use STEM, STEM, and then we are using bar, right? Now, bar has a lot more usage, right? Because when we are using this bar function, what is happening is it is giving me control over the sequence number and the height, right? So this gives me an idea that if I can change where this bar is going to start from and how far it is going to go, I might be able to create different kinds of graphs using it, right? And in case any of you thought about it, this kind of brings us to what is called stacked bar graphs, right? Now with stacked bar graphs, what is different? The setup remains the same. I have kept the grid on, so let that be. What is changing? What is the new code that is coming in? The first part remains the same, right? Which is I am creating, the first marks was for mid-sem marks, right? Say, for example, we're using mid-sem marks over here. I'm using a sequence number and the height I'm setting up to the mid-sem marks list. And it will help me generate this blue part of the graph, right? Just like we were doing over here, right? Here we were doing total marks. Instead of total marks, we're doing mid-sem marks. But exactly the same thing we are repeating over here. So that gives me the blue part of the graph, right? Then I'm going to get a little creative over here. How am I going to get creative? I'm going to bring in another parameter of the bar function, right? Which is bottom. So far we have been using height because we have, when we are using just height, it assumes that bottom is always 0. But it might not necessarily be the case. So now what I'm saying is the height is the end-sem marks and the bottom is mid-sem marks, which means that for each of these orange boxes that I'm creating, it will start from the top of the mid-sem marks and have a height corresponding to the end-sem marks. That's what it means. And by just creatively, and what is happening over here is I have just creatively positioned 2 plots on top of each other so that it looks like a cluster, so that it looks like a stack, right? And I can create multiple such stacks, one on top of another, right? That's the benefit of being able to create, that's the benefit of being able to have complete control over the graphing functionalities, right? Just to demonstrate that by adding the mid-sem and the end-sem marks, we should come to the total marks. I have created the bottom part and the top part using the given marks, right? The midsem marks and the endsem marks, and I have also put this plot, which is these dots that I have put. It is coming from a third plot where I am using the total marks. So you can very well see that these two points are computed using two different pathways. One is we are getting directly from total marks. The other is being computed as the geometrical sum of the midsem and the endsem marks. And you will see that both of them adds up to the same point. That is why I wanted to demonstrate this, right? That whether you are, that the value that you get over here is actually correct, right? So these are called stacked bar graphs. Now, while this is an interesting representation and it is good for quantitative measures, right? It may not help me understand whether a student did their best, right? What is the proportional contribution of their scores, right? And that is where a new kind of graph can be created called a proportional bar graph, right? Or a proportional sales graph, right? So what it is showing is the percentage contribution of the endsem and final sem marks in the total marks of the student, right? If I look at, for example, how do I know that this is true? Because if I go to this particular graph, I see that student 10 has scored 0 on the endsem and 1 on the finals, right? Probably he was absent, right? I don't know. But the same graph, when it shows up, then 100% of the marks is contributed by the endsem itself, right? We had 0 contribution in the finals, right? So we see that these graphs are definitely correlated, and it gives us a different kind of visualization, a different kind of insight about the figure, right? It tells me who was essentially absent for the endsem or the midsem, right? How am I going to create this graph? Well, I have to create a proportional value, right? All other things remaining the same. I now need something called a midsem proportion and final proportion. We are going to create a stacked bar graph like before, but the values in those stacks are going to be different. They are going to be proportionate to the marks that a student got, right? So when I'm talking about proportions, I need to calculate these proportions. How am I going to calculate the proportions? Well, for every student, all I'm going to do is I'm going to sum up their marks, their final marks and their endsem marks, which is their total marks, and I'm going to look at the proportion of their final score, their midsem scores by total scores, and the proportion of their and 100 minus that. I mean that this could easily give me max marks minus the proportionate score. That could give me the midsem, the final proportions, right? So this allows me to now create two graphable lists, right, which I'm now going to use and plot them as bars, right? In the first bar, I have my sequence number set to the original sequence number and the height set to midsem proportion. That is the change. So the proportion will go up over here. And then I have the final proportion built on top of that. So two graphs like before to show the stack, except that the stack values will always add up to 100% or 1 in this case, right? So that's a proportional bar graph, right? Now, in many cases, what may happen is this representation is great. It allows me to see things on top of each other. But what if I wanted to make a more apples to apples comparison, a more of midsem to midsem and finals to finals kind of a comparison, right? In that case, what I will be using is something called a clustered bar graph, right? Now, the core concept of a clustered bar graph from a visual perspective is that it is a bar graph, but its width, if I'm making a cluster of two elements, then the width of the bar graph should be at least half the original one, right? That's the key idea. And now the bar graph has to be, one of the the blue graph, for example, has to be shifted to the left, and the orange graph has to be shifted to the right. How much? By exactly your original graph would, if I had just created a bar graph, that bar would have come up over here. It would have taken the whole space. Instead of that, what I'm doing is I'm moving it on the side. So this graph has moved 0.25 on the left. The orange graph has moved 0.25 unit to the right. That's the way we plot clustered graph and create composites on top of it, right? So all that I'm going to do is, from every sequence number, I am going to deduct bar width by 2, right? Bar width by 2 for every element. So if this element was supposed to have been, so let's pick another one. If this element was supposed to have been centered around here, right, at 13, I'm now centering it at 13 minus bar width by 2. Bar width is 1 unit, so half unit of that. Oh, I've given a bar width. I've given a bar width of 0.4, so it is going 0.2 on this side, and it is going to add 0.2 for the orange graphs. So all I have are two graphs that are created. The first one is the blue graph, the second one is the orange graph, and they have just been printed one after another so that it looks like a clustered representation, right? And I have my total marks from before that have also plotted, just to demonstrate that you can create pretty complex graphing structures just by overlaying graphs on top of each other. That is very, very important, right? Now, in many cases, what may happen is, while you can represent information like this, right, you may also want to segregate out this information into 3 distinct pieces, right? If I have 3 graphs over here, you can come to me and tell me that, hey, why don't we separate it out into 3 different graphs, right? And that is exactly what subplots allow us to do. So far, we have been working with a plot, right? We have been working with a plot. Now, it may happen that I want to have multiple subplots within a plot, right? And this is where I can do that. So creating of subplots allows me to separate the midsem marks, final marks, and total marks as 3 different graphs itself. What changes? Well, first of all, I need to create subplots. I need to tell it that I want to create 1 row of 3 subplots where the figure size kind of remains the same as before, right? If I want to share the X or I want to share the Y is false, means that there are no common axes over here, right? If this was true, then these 2 axes would have been combined. There would have been 1 axis mentioned and there would be no labeling on the other axis, right? But we don't want that. We want 3 of them to have independent axes, so that is fine. After setting the figure to have subplots, what you will notice is I get a figure object and I get the 3 axes. I get AX1, AX2, AX3 as a list itself, right? So I can access, if I have to do any functionality on this particular subplot, I can always access it using the AX1, which is this handle. And then I have my axes, bar, set ticks, Y labels, right? Whatever I wanted to do, all those options are also available within the subplot itself, right? So this kind of gets us into subplots, right? Now, we are running a little short on time, so I'm going to probably quickly rush through the next section and probably take a few questions, right? While we covered many of the basic charts and its annotations, there are different requirements for advanced visualization, right? As we discussed beforehand, the purpose of visualization is for data exploration and analysis, right? It allows us to look at communication and presentation for pattern recognition, insight generation, storytelling, and narrative generation, right? So when I talk about data exploration and analysis, right, visualization is allowing us to, to do an exploratory view of the data itself, and all these graphs that we saw so far, right, they are essentially allowing us to do this kind of exploratory analysis, right? Now, in many cases, we may want a particular type of a graph or a visualization to make it easier to present the data to an audience, right? Whether you are presenting this data to the general public or to your colleagues, by presenting it in a format where complex information is kind of showcased in a particular graph itself, it makes it easier. And there are different types of graphs that you can bring in over here, right? For example, there is something called a waterfall chart. So for example, your final question, your final marks depended on, there were 6 questions in your paper with positive and negative markings, right? And the cumulative scores are taken. So the first question was +10, the next question was -3, the next question was 7, the next question was 5, and I have added it all up to a final total, right? So this kind of a representation, which is showing the cumulative effect of subsequent data points, is called a waterfall, right? Very, very good when it comes to representing information that is changing, where some cumulative value is changing as new inputs are coming in. This kind of a waterfall chart, you will understand that it is very, very easy to build, right? All I need to do is, this is a box plot. The basic philosophy behind this chart is that I have a box plot. Every subsequent value, if my value is a negative value, I set the height as, I know my height, right? So I start off from the previous one's top minus height as the bottom and grow for a height. If this is a positive value, then I start from the bottom and add the height. That's the rule that I follow, right? And I can keep on doing that multiple times in order to generate a visualization like this, right? We can have range charts, right? If we wanted to do, say, for example, range chart of gender performance, right? So I have the range of marks obtained by the female students and the male students in the mid-sems, and the same graph for the end-sems. And I can now compare if the ranges are changing dramatically, right? So this is another way of representing information, right? In many cases, the information may become more prominent if I, instead of representing the information in a linear scale, I represented the information in a polar scale, right? In that case, something that is really big or something that is repetitive tends to become more emergent, right? So this is essentially where the only change that this needs is to set the axes as a polar coordinates, right? And do essentially a stem plot on top of it, right? Instead of a stem plot, if I do a bar plot, then I get another kind of a graph, which we commonly call sunburst charts, right? And these sunburst charts, they're visually very, very exciting, right? You can have alternate colors on them so that it looks even more interesting, right? But it is essentially the line graph that we have from previous, right? The same student scores, the student marks, the student ID, and the student marks that has been shown in a different way, right? I might also have a situation where I needed to perhaps do a box plot where, along with the distribution, along with particular subjects, for example, what is the mean of a subject, what is the standard deviation or the error margins within a particular subject, if I want to demonstrate that. So I can create a box plot with a notch, right? This is called a notch, and I can have a whiskers on both sides, right? In order to create a box plot. Joining points together in a radial graph gives me something called a radar plot, right? So it can demonstrate areas of competency, right? If there are multiple points where I wanted to focus on, and I wanted to compare and have a relative comparison of multiple parameters from two different individuals, then their radar plots might be really, really useful, right? So these are just different ways of representing the data so that it brings out the point that you are trying to make, right? Another aspect is on the pattern recognition and insight generation part. This is where statistical tools tend to help quite a bit. And not only, the importance of statistical tools is that you can now start to do a lot of annotations. We have seen this graph previously where we had a subplot of the midsem marks, final marks, and total marks. And now notice that I can now add specific annotations. I can add specific statistical summaries. I can point out things which are of interest, right? I can have this arrow over here. I can mark out a band of different colors saying that, this is of an area of interest to me, right? So I can start to get into more statistical processing of that data, looking at things like density functions, cumulative district density functions, right? Percentile scores on top of that, histograms for that matter, using that information to map in regression information, trend lines on top of the data set itself, right? So I can definitely, that's the demonstration of how to use visualization for more statistical purposes. In many cases, the reason you use visualization is to tell a story, right? And the story can be very different, right? For example, if I wanted to tell a story of the class, right, where I have a bubble plot of the student scores, I can plot multi-dimensional representation, right? I had six dimensions in the data, right? Sequence number, I had student IDs. So what I'm doing is I'm saying that, okay, let the bubble color be for gender. So I have blue or orange based on the gender. So I'm using one dimension over there. I have the bubble size, which is proportional to the score, right? So bigger bubbles have bigger scores, smaller bubbles have smaller scores. Then I can have the bubble label for student ID. So that's a third dimension that is getting mapped, right? Then I have the XY. Then I can have the bubble transparency mean something else, right? So the more transparent numbers could mean that they have poorer marks, poorer presentation. So I can use the transparency, the edge colors of each of these bubbles, right, to mean something else. This is how I can have multiple dimensions. And even though a graph itself has only two dimensions, X and Y, representing information on the graph, I can take the help of multiple parameters: the transparency of the bubbles, the size of the bubbles, the color of the bubbles, the line width of the bubbles, the edge width of the bubbles, the edge colors of the bubbles, right? The labels in the bubbles, right? So there are multiple dimensions that can be folded into in order to tell a particular story. That was important, right? So it's almost time. And so I finally wanted to say that all this information is needed because data visualization kind of enables these data-driven decision makings by providing a very clear and concise representation of information, right? So these data visualization techniques and tools, they vary based on the type of data and the purpose of visualization, right? But at the end of the day, I did not get into heat maps and geospatial distributions, right? There are network distributions that can be created, but there are waffle diagrams, right? So there are many more graph types that are available, but I wanted to leave you with the notion that controlling a graph is almost like creating creating this visualization is like almost doing it bottoms up. You have to first think through what is the point that you are trying to make, and accordingly you create the visualization, right? So it's almost like a story. It is almost like an art of storytelling, an art of visualization. And that can only be developed once you have the technical competence, the control over the tools in order to master that craft, right? So with that, I will take questions.
Yeah. Thank you, sir. Thank you for the valuable session. I hope students also enjoy the session and they learn a lot of things about Matplotlib, because the image, the picture can say millions of informations that we cannot simply describe as a text. So the reason we are using a data visualization techniques in a different phases in any data science or machine learning applications. So this is very essential, and students today they got to know different plotting techniques which you introduced, and your presentation also is like well organized, and we are very thankful for that. for the effort you made, the presentation. And surely we will discuss and if we utilize the information in our application like a projects or wherever is possible. We'll surely utilize that. And uh, uh, because of this presentation and your effort, we are saying a thank you, sir. So thank you for your.
You're all very, very welcome.
Yes.
Thank you. Thank you all for tuning in today. I hope to see you all soon.